Hypothesis testing. A lot of what we do in stats, in quantitative methods, is try to understand whether or not a relationship exists. And we start with a research question, right? Is X related to Y? Is gender related to income? Are social ties related to protest participation? We take that a step further and develop a hypothesis, right? The hypothesis, which is a directional statement saying, for instance, people with more friends are going to be more likely to engage in protest activity, right? And we have academic literature and theory to explain why we think that hypothesis would play out compared to alternative hypotheses. So we create hypotheses and we want to test them against the idea that in a real world situation, we're trying to see if there is an effect of X on Y, is an effect of having friends on protest participation versus not, right? So we take that logic to statistical relationships with us and we say we want to compare, is something going on versus is something not going on. Hypothesis testing helps us provide evidence that our theory, our research question, or our hypothesis is correct. We want to demonstrate that whether or not there is a relationship between two variables, and that can be in the form of, like X is related to Y, or some level of X is related to Y, right? Some change in X is related to some change in Y. Changing the amount of friends I have might change my likelihood of protest participation, for instance. Moreover, not only do we want to see if there's a relationship that exists amongst our sample, but we're testing that against a hypothetical probability distribution. We're saying, if we are to find a relationship, we want to ensure that this relationship would also exist in the population, right? We can find something in our sample, right? But we have to compare our findings against theoretical probability distributions to see if our findings are simply due to chance or to something other than chance. We call that sampling error. So we want to see if our difference or our relationship reflects a true relationship that would exist in the population. To see if there is a relationship, we don't just go out into the field and start looking for evidence that a relationship exists, right? Rather, we start with the assumption that no relationship exists. And we try to tack on or tally up evidence against the assumption that no relationship exists. So we're trying to find further and further evidence against there being no relationship. So we start with no relationship exists, and we look for evidence that no relationship does not exist. We're looking for the negation of no relationship. Let's say we were trying to test if somebody's drunk, but we didn't have a breathalyzer. How would we do that? Well, there are a lot of signals of somebody being drunk, right? A lot of us can think of it. Oftentimes you can just smell the alcohol in somebody, but there are a lot of different signals of whether or not somebody's drunk. Here I have a couple. Let's say you wanted to test if somebody's drunk and you don't have a breathalyzer. You might say, well, are they walking straight? Are they not slurring when they're speaking? Are they attentive when you're talking to them? They're not like eyes crossing. They're responsive to your questions. They don't smell of alcohol, and they can maintain balance while they're standing. Right? All of these things would be indicators of not being drunk. So for us, we start with the assumption that somebody's not drunk, and we start tacking on evidence to say, well, this is an indication that you might not be not drunk. You might not be sober. So you start tacking on, and as you get further and further away, start piling on more and more evidence of not being drunk. That gives you more and more suggested evidence that they might not be sober, that they might be drunk. And you can think about this like, let's say we have a normal distribution, right? And in the middle, we're going to say we have this assumption that you're not drunk. And what you're doing is you're tallying on or piling on evidence against that, right? So let's say you ask somebody if they're walking straight. Okay, check mark. Okay, they're probably sober. Let's see if they have no slur in their speech. Oh, well, this person is slurring their speech. So let's say we're going to tack on one thing. So we're going to move further this way. Okay. Are they attentive? No, they don't seem attentive. Okay, that's more evidence this way, right? Are they responsive? Not really. Do they smell of alcohol? Yes. Okay, like more and more evidence. So you're getting further and further away from this assumption that they're sober, right? So you can think of it that way, as sort of on a sort of a scale, right? Like, so you're getting further and further away from some ideal point. So with that in mind, we first develop a hypothesis or an idea, an assumption that nothing exists, that no relationship exists between these variables, or moreover, no difference exists. And this is particularly important when it comes to testing mean differences or when we're thinking about the t-test, right? And what you're trying to do is You're trying to set up that initial hypothesis, the sober hypothesis, right in the middle. And what we hope to do is to, what I say here is disprove or reject that, right? And how do you reject that? You tack on more and more evidence as you get further and further away, right? This initial hypothesis that nothing exists, that no relationship exists, is called the null hypothesis. No relationship, null, no, null. That's how you remember it. It's our initial hypothesis. Next, you develop a contradictory hypothesis known as the alternative hypothesis or research hypothesis. That hypothesis is that something does exist, or a relationship does exist between these variables, or a mean difference does exist, right? And what you do with this alternative hypothesis is you put it at the tails of the distribution. So we think of a normal curve. In the middle, we're going to have the null hypothesis, and you're getting further and further away. On either side, right, you get closer and closer to the research hypothesis. As you tack on, you get further and further away from the null and closer to the alternative or research hypothesis. To demonstrate that a relationship does exist, like I've already said, to demonstrate that a mean difference or that something does exist, we look for what we call extreme evidence against the null. Extreme evidence that no relationship does not exist. Extreme evidence means I want to be further and further and further and further and further and further away from that null hypothesis. So what I mean by extreme is we want to be way out in the tails. We want to be really close to where we put the alternative hypothesis. That will come in handy when we start thinking about the hypothesis test as a distribution, right? We want to be in the tails of that distribution. We want to be really far away from the null. As we get further and further away, it provides more and more evidence against that null. It means that there's a lower likelihood that the null is going to be true, and it allows us to disprove or reject the null. That's what we want to do. If we want to provide support for our research hypothesis, we want to reject the null, right? We want to say that this idea that nothing exists or no relationship exists or that there's no mean difference doesn't fit for our case. We found enough evidence against that. We are out in the extremes of the tails of this distribution that we say that the null is probably not true for our case. So I say we're looking for extreme evidence, right? We want to be out in the tails of that distribution, but what counts as extreme? I do want to point out that hypothesis testing is built for bivariate and multivariate relationships. We can't really do hypothesis testing with univariate stuff because we're only describing one specific variable. Show you this to highlight where we're going. I created a 2x2 table here that breaks down levels of measurement and whether or not we're looking at the independent versus the dependent variable. We know the dependent variable is the outcome variable. We know the independent variable is the predictor. So we have 4 tests listed here. We'll start here with the lowest level of measurement. We have a chi-square test of independence. Here we're looking for whether or not a relationship exists between 2 variables, but the level of measurement of those variables is nominal or ordinal. When we get down to this t-test, we're looking at mean differences, whether or not a mean difference exists between 2 groups. So we're looking at one grouping variable, which is nominal or ordinal, and then one interval ratio outcome variable, right? So we can calculate a mean, let's say mean happiness score or mean income, and we want to break that down and compare groups. Let's say we wanted to compare whites and others, or we wanted to compare working class and everyone else. We can look at income based on these class levels, right? The important thing to remember about the t-test, however, is that when we're comparing groups, we're only looking at 2 groups, right? We can only compare 2 groups when we're looking at a t-test. So we're looking at mean income for working class individuals compared to mean income for middle class individuals. If we wanted to add a 3rd group, we could do that, but we would need a different test, right? And that different test is called analysis of variance. So the analysis of variance is an extension of the t-test in which we have a 3rd or 4th or 5th or however many you want number of groups, right? So it's 3 or more groups that you're comparing on some interval ratio outcome. You're looking at a mean difference between these groups. And then finally, much like the chi-square, which looks at whether or not there's a relationship, the correlation also looks at whether or not there's a relationship between variables. However, this time, instead of nominal and ordinal variables, we're looking at only interval ratio variables, right? So you can cluster them in terms of like increasing sophistication for the level of measurement, going from chi-square all the way to correlation, or you can cluster them in terms of what their hypotheses are trying to determine, right? The hypothesis tests for chi-square and correlation are going to be about whether a relationship exists. T-test and ANOVA, while they are looking for whether or not a relationship exists, the real test is whether or not a mean difference exists. Right? So T-test and ANOVA are mean difference, chi-square and correlation are relationships.
Thank
you. Mm-hmm. T-test, we're testing the difference between means of two groups. ANOVA would be testing the difference between means of 3 or more groups. Often in the social sciences, we're trying to understand differences, right? Are these groups different from one another, right? Even if I look back at like some of my work on protest participation, I was interested in comparing non-participants to participants, right? How do they differ from one another? Do participants have certain characteristics that non-participants don't? So a lot of what we do is comparative work. We're looking at comparing groups with one another. We have an example here. Let's say a gerontologist. A gerontologist is somebody who studies the aging population. If a gerontologist wanted to test two methods for increasing memory, let's say they went out and they wanted to test these two methods by going to nursing homes and sampling some individuals and saying, okay, we want to see if method A versus method B helps to improve recall or memory amongst these residents. They can do that. So again, this is along the lines of comparing groups. They randomly select 10 residents from these nursing homes. They divide them into method A and method B. Method A has participants engage in memory games on an iPad. So they hand them an iPad, say, do these memory games for a certain amount of time a day. Method B is a control group that all they do is simply journal. And they want to see, do these memory games, do they help improve recall? So after some period of time, they asked both groups, all 10 participants, to take a recall test. Right? And at the end, we find that the mean for group A, the memory games on an iPad group, had a mean recall of 82, right? So let's say this is scaled from 0 to 100. They had a mean recall of 82. Group B, the daily journal group, had a mean recall of 77. Now we might ask, is this a difference? Well, if we look, 82 and 77 are not the same, right? So if we can agree on that, we know that like there is a difference going on. Now the next question is this a true difference that we would find in the population? If we ask ourselves further, is it an extreme enough difference that we can say in the population, this is a true difference that we would find? This is not just what we call sampling error. This is not just chance. Without a statistical test, we would have to use some logic here. If you look at the scores, method A is consistently in the low 80s, right? 80, 82, 83. Method B consistently in the high 70s, 76, 77, 78. However, we notice that this may not be because of sampling error because there's so much closeness in the scores, right? 82, 80, and 83 are pretty close. 76, 77, 78, really close. And there's no overlap between groups, right? People in group B aren't having low 80 scores, right? And people in group A aren't having high 70 scores, right? So there's not only homogeneity or closeness in the scores, but there's no overlap. So there are two distinct groups, right? The means are two distinct. Like if we were to draw the ranges as distributions, there would be no overlap. So based on this just simple logic, we could probably say method A is probably better, but we still have to go out and run a statistical test to see if this is truly something that we would find in the population. Right? So we have to do a statistical hypothesis test to see if this is truly a difference or just sampling error. Another example, do conservatives and liberals differ in the severity of their discipline styles for their children? Right? Telling your kid to go to their room or punishing them by saying, okay, no TV tonight or no TV for a week, all the way to like having dinner or not having lunch, all the way to physical discipline, right? Do these two groups differ? And what we can do is create a scale from 0 to 100 or 1 to 100, however we want to do it, where 100 would indicate very severe styles. So we can say every time somebody's done some kind of disciplinary action to their children, that would count as more severe. Right? So first off, just from the statement, we know that this is a bivariate relationship, right? We have a variable that's composed of conservatives and liberals, right? We know that. And we know that another variable is severity of discipline, right? So we have two variables. One is political orientation, of which the categories are conservatives, liberals, and severity of discipline styles. We know that the categories in there is a range, it's a scale from 0 to 100. So what we can do is compare these groups. We can say, okay, what is the mean severity for conservatives? What is the mean severity for liberals? And see, is there a difference? Much like we did for the example for the gerontologist and the memory recall, right? We can calculate those means and see if they're different. And if it's an extreme difference, we'd say, okay, this is probably something we'd find in the population. But again, we have to figure out what counts as extreme. Another way of asking this same question is there a difference in mean severity between liberals and conservatives? So keep that in mind when we get to doing t-tests and ANOVA. We're concerned with whether or not there's a mean difference. Let's say we collected the data. We don't know how many people we collected this from just yet, but let's say we did collect the data. And we said out of 100, liberals had a mean severity of 54, conservatives had a mean severity of 58. This means that conservatives were more severe in their disciplinary style. We can see that from these data here. But now we want to see, is this difference large enough to count as a true difference that we would expect in the population? These are just data from our sample. So to demonstrate that the mean difference truly does exist, we look for evidence against the null, meaning we're looking for evidence against no mean difference exists. And then we can see, is this difference extreme enough? Is this difference of 58 to 54, is it extreme enough? The null hypothesis for a t-test is that there's no mean difference between the two groups in the population. Or alternatively, that the mean of one group is equal to the mean of the other group in the population. So in the population, we would expect that these two groups should have the same mean severity. The null hypothesis is that liberals and conservatives have the same mean severity. Formally written out, it is H naught is represented by mu1 equals mu2. So H naught is how we write out the null hypothesis, H sub 0. Mu1 is the mean of group 1 in the population, and then mu2 is mean of group 2 in the population. An important thing to recognize here is that while the null hypothesis states that there's no mean difference, if we do find a difference, it's not automatically that it can be attributed to a true population difference. The null at its core would blame any difference on sampling error, right? Remember, we're looking at a total distribution here, and we're saying in the middle is the null. So let's say we tacked on, one line of evidence. Is that enough? Well, the null would say that still counts as the null, right? It's still close to the null, right? We're just going to blame it on bias. We're going to blame it on sampling error. If we were to take the true population, you would find that these two means are going to be equal, right? The difference would be 0. You just happen to find in your sample a small difference. It's not enough, right? So any difference, the null is essentially going to blame on sampling error. Next, we have the alternative hypothesis. Remember, the null's in the middle, the alternative's at the tails. The alternative is that there is a mean difference between these two groups in the population, and that the mean of one group does not equal the mean of the other group in the population. Again, formally, H sub 1, sometimes it's written as H sub A as alternative, and it is that mu1 does not equal mu2. So in the population, group 1's mean should not equal group 2's mean. So much like the null hypothesis would blame every small difference, every difference no matter what, it's just bias, it's just sampling error. The alternative hypothesis, the research hypothesis, blames every difference on, hey, that could be a true population difference. These are two hypotheses that are competing with one another to either blame it on sampling error, on chance, or to blame it on a true population difference. So we're trying to get closer to seeing if it is a true population difference or is it closer to being just chance. So some questions that we use to proceed. When we're examining this difference, we want to see, is this difference 0? Let's say we calculate means for two groups and we ask ourselves, is the difference 0? More often than not, the difference isn't going to be 0, right? If there might be some slight difference, And that's because of variability. You have a lot of people. Let's say we took the mean age of this class and then we took the mean age of my Monday class. There's going to be variability, right? The chances are we're not going to have the same mean age. So is the difference zero? More often than not, it's not going to be zero. But the next set of questions is important. If it's not zero, we need to ask ourselves, is that difference small or is it large? Is it small, close to zero, or is it extreme, right? If it's small, we can say, okay, it might be due to chance. If it's large, we might say that it may be a true population difference or a true difference that we've seen in the population. But again, we need to figure out how large is large enough, how extreme is extreme enough of a difference to count as a true difference. If we're trying to figure out what's large enough, if it's a large enough difference, we can take our knowledge of that distribution, the knowledge of the null being likely in the middle, the knowledge that the alternative hypothesis is going to be at the tails, and our knowledge of how the normal distribution and z-scores work together to create z-scores for mean differences. So we can create a z-score for a mean difference of 0. We can create a z-score for a mean difference of 30, right? Just like we did for raw scores, right? If we remember, to calculate a z-score, it's somebody's raw score minus the mean of that group over the standard deviation of that group, right? And that tells us where somebody's raw score falls relative to everybody in that group, right? Everybody in that distribution, right? You might be 2 standard deviation steps above the mean or 2 standard deviations below the mean, so on and so forth. But that tells you where in that distribution you fall. Are you above everybody, right? If you're on the top end of that distribution, you're higher than the mean, right? You're higher than people below the mean, right? Same thing for if you're on the bottom end, right? You're way low, right? There are so many people above you. So we can take that knowledge instead of using raw scores, we can convert mean differences into z-scores. If we had a large z-score, it would indicate to us that we are extreme deviations from the mean, the 0 mean difference, the null hypothesis at the middle, we'd be out in the tails of the distribution, right? So we can take that logic and apply it that way. Then we can ask, what is the probability of getting this extreme of a score given that the null hypothesis is true? And if we remember, we can break up a normal distribution into 68, 95, and 99%, right? Because how much percent is under the curve? 100. 100% is under the curve, right? It's asymptotic, but it's implied that 100% is under the curve, right? So what we can do is take that logic and say, well, if 95% is between negative 1.96 and positive 1.96, that means that 5% is in the tails, right? So we take that same logic and apply it to z-scores and see how likely is this extreme of a score, right? So we'll see how we get there, but we can use z-scores to answer those questions, right? The likelihood of finding this score or greater or more extreme of a difference. Distributions and z-scores. So we're going to need this to help us to figure out if a mean difference is extreme or not. So let's rely on our example 2 still. We want to compare differences in child rearing discipline severity, again, by political orientation. So our X variable, our independent variable, our predictor, our grouping variable is going to be political orientation. We have conservatives and liberals. We have our outcome variable, which is severity. Severity, okay, here it ranges from 1 to 100. 1 meaning less severe, 100 meaning more severe. We give this to one random sample of 2 groups, right? We take 60 people, 30 randomly selected conservatives, 30 randomly selected liberals, and we calculate their mean severity, right? Maybe it's a self-report where they mark how many ways in which they've disciplined their children. Maybe we have observations of these people over a year to calculate these things, but it doesn't matter. We collected the data, we got it. And again, we calculated the conservative mean severity was 58, liberal mean severity was 54, and the difference between these groups, between conservative and liberal, is positive 4, right? Conservative 58 minus 54 is 4. Now we ask, is this a true difference that would occur in the population, right? That's what we're trying to answer. Is this something that would truly happen in the population, or is this just sampling error? Well, what we didn't cover in this class, but is important to quickly go over, is we apply the logic of normal distributions to sampling distributions. The idea here is we just took one sample, right? We have 30 liberals, 30 conservatives. We got that mean. In an ideal world, we would take one sample, calculate a mean, and then throw them back out there, take another sample, calculate the means for each group, and then throw them back out there, right? And what we could do is plot the means for each of those samples. Let's say we just clumped liberals and conservatives together. 60 people, we took a sample, we took a mean severity, plotted that mean. Then we threw them out there, took another random sample of 60, plotted that mean back, and we did that 100 times. Some of our means would be low, right? Some of them would have a mean severity of 0. Some would have mean severity of 100, but a lot would be somewhere in the middle, right? Most would be somewhere in the middle. And if we think about it, if we did that theoretically over and over and over until infinity, what we should find is that we could plot all of those means, and the means would look much like a normal distribution. Most means would cluster around the center, right? Around some mean score. And then there would be few scores that are at the extremes, right? We can apply that same logic of sampling distributions of means, right? That's what we would construct. That would be the sampling distribution of plotting means. We can do that same thing for sampling distributions of differences between means. So now instead of taking a sample and calculating the mean severity, we're saying, let's take a sample of 60 people, break them into conservatives and liberals, and say mean for conservative, mean for liberals, calculate the difference, then plot that difference. Then we're going to do it again for another sample of 60, 30, 30, mean, difference, plot that difference, right? So we're going to do that over and over and over again, infinity times. And much like a normal distribution, much like a sampling distribution of means, we should be able to plot that sampling distribution of differences. And that should look like another normal distribution. The differences would tend to cluster around a mean difference of 0, but some differences are going to be larger than others, right? Here we have a mean difference of 4, but we could find a mean difference of 30, right? A mean difference of negative 30, right? Meaning we have one group that's lower than the other if we're taking these differences, right? So what we can do is, with this logic, we can construct a theoretical distribution of all those samples, and then we can convert our difference of 4 into a z-score. Just like we said before, we can convert that difference of 4 into a z-score and plot that relative to all possible mean differences. And we can see how extreme is our mean difference of 4 relative to all possible theoretical mean differences. Mean differences of 0, mean differences of 30, mean differences of negative 30. So what we do, we took one pair of random samples, we have a difference of 4, then assume we took 70 pairs of random samples, each with 30 conservative, 30 liberal, and we calculate the difference between means. So each score here represents a difference score. So we had a difference of 4, right? 58 minus 54, and that gave us a positive score, right? Positive 4. Everybody see me circling that positive 4 there? Let's say that that's the one we calculated. So we threw those cases back out, those observations of 30 and 30 back out. Then we took another sample. We took the mean of conservatives, took the mean of liberals minus liberals from conservatives, and we had negative 2. What that would mean is that, okay, we take conservatives first minus liberals. That would mean that liberals had a higher score than conservatives, right? We don't know what those scores are, right? It could be 60 and 58. It could be 62 and 60, right? But all we know is liberals in this case, the second group, were higher, which is why we have a negative 2. What does this score of 0 represent? Same mean. If they are the same mean, they fall along the lines of the what? The null hypothesis, exactly, right? So a mean difference of 0 would fall exactly at what the null hypothesis would expect. Normally, it's not going to be this pretty, right? You're going to have non-integers, right? Decimal points that you're going to have to be dealing with. You might be really close or really far from 0. But generally, what you're going to find is you can plot all of these into a distribution. It might look something like this, where most scores tend to cluster around a mean difference of 0. And you have few scores at the tails, right? Few scores at the high end of a mean difference of 5, few scores at the low end of mean difference of negative 5. This here approximates what we would expect from a normal curve, right? It's an ugly normal curve, but it's close to a normal curve. This curve also approximates that null hypothesis, right? Where the null is in the center and we see these few extreme scores out there in the tails. Null hypothesis of no mean difference, where the mean difference tends to center around 0. And if we recall, we can take that information about distributions and think about where these scores fall in relation to other scores, right? We can take a normal distribution and break it into standard deviation units, or z-scores, right? Z-scores are standard deviation units. So we know +1 standard deviation, +1z, -1z. We know that 68% of cases fall between those two, -2 to +2, 95.44, 99.74. Right? So we can take that logic and apply it to that distribution of differences between means to figure out where our difference falls, right? If we look back at this, we know that our difference of 4 falls out here. But we don't know if 4 is like an extreme score. We know it looks like it's an extreme score, but if we convert that to a z-score, we can standardize that score to see how far it is. And we can use that standardized score to figure out a probability, right? If we cut this off here and just say we scored 4 here, we don't know what probability or what proportion, what percentage of cases fall in that tail, right? But if we take information from this distribution of the differences between means and standardize them, we know if we standardize, we're basically creating a normal distribution, and we know that there are rules about the normal distribution, right? We have the mean, mode, and median at the center. We have standard deviation units that we can break it up. We can figure out proportions of cases at each point. So that's the next step, is converting this to a standardized or a standard normal distribution. Here, recall, this is what the standard, the normal curve looks like. We see sigma there, but if we were to apply our differences, right, we're looking at mean differences, we're plotting mean differences, the normal distribution looks a little bit different. It's the same, but the subscript changes, right? Watch the subscript change here. It goes from -1 sigma to -1 sigma x bar 1 minus x bar 2. We have the mean of group 1 and the mean of group 2. So now what this is saying is the standard deviation of a distribution of differences. Remember, each one of these steps is a standard deviation. So here we're looking at the standard deviation for the sampling distribution of differences between means. So again, evidence against the null, right? Which means we need extreme scores. Extreme scores mean extreme mean differences. It's more evidence against the null. That means it's further away from the null. That also implies extreme z-scores, right? Really high z-scores. The higher the z-score, the further and further away we are from the center, the further and further we are from the null, which means that there's a lower likelihood that the null is true. But again, what counts as extreme? We want to figure out where our difference of 4 falls relative to everybody else. So I know there's a lot on this page, but I'm just walking you through steps that way you have for reference. So let me walk you through the steps. We have a z-score formula, right? We know it's x minus the mean of the population over the standard deviation of the population. So this is a raw score relative to the population, or a probability distribution. However, oftentimes we're not working with the mean of the population and the standard deviation of the population. Since we're talking about means and not raw scores, what we're going to do is replace that x with an x bar, right? So instead of comparing my raw score to the mean of the population, we're now going to compare my mean of my group to the mean of the population. But we're not doing means. We're doing sampling distribution of differences, right? Sampling distribution of differences between two group means. So instead of just dealing with one group mean, or our sample mean, we're looking at group 1 and group 2 in sample 1, right? So we're saying, instead of using a raw score x or one mean for our overall sample, what we're going to do is take the mean of group 1 minus the mean of group 2. And that's what we see here. We're going to replace this x bar with mean of group 1 minus the mean of group 2. Right? If you'll notice, in each one of these denominators, we're changing based on the distribution we're using, right? So here we're using a probability distribution, which implies sigma and mu, the mean and the standard deviation of the probability distribution. Here, when we're looking at the sampling distribution of means, we still have a mean, a mu, but the standard deviation is the standard deviation of means, right? Sigma of the sampling distribution of means. Now, when we replace this with differences, we also replace sigma with a difference subscript, right? So it's the standard deviation of the sampling distribution of the differences between means. If we recall, when we plotted that difference plot, what was the most common or most common occurring score? Right at the center. It was the null hypothesis. It was a mean difference of 0. Well, if we know that the mean should be, and the null hypothesis implies 0, we can plug in 0 as our mean, as our hypothetical mean, right? It's expected, right? The null would expect that nothing's going on, and we're comparing against the idea that nothing's going on, right? So we plug in the mean difference of 0. When we subtract 0 from anything, what is that? It's the same thing. So our z-score calculation is x bar 1 minus x bar 2 over the standard deviation of the sampling distribution of the differences between means. Here's our calculation. We can take a mean of group 1, a mean of group 2, and then some standard deviation. It's important to know this is still an unknown parameter. Why is that? Well, first off, when we were calculating z-scores for our sample, we had to plug in SD, right? Or we had to plug in standard error of the mean because we were only using our sample. We had to plug in our mean of our sample because we didn't have mu. So now you're telling me I got to calculate this z-score with some standard deviation of a population, right? Or a sampling distribution of differences between means. I didn't take 20 million samples. I took one sample of 2 groups, right? So this is still unknown. We don't have this information, but as you'll see, we have to plug in something different, right? So oftentimes, and by oftentimes I mean just in the next set of slides, I'll just provide you with this, right? Because this is still unknown. We can plug in a value to estimate or approximate that. So let's take our example. Discipline severity, conservative mean is 58, liberal mean is 54, the difference is positive 4. Let's say that I just gave you that standard deviation of the sampling distribution of the differences between means. That's sigma sub x bar 1 minus x bar 2. I said it's unknown because we don't have that sampling distribution of the differences between means. So I'm just going to tell you it's 2. Hypothetically, I gave you it's 2. Now, since I have that information, it's no longer unknown, we can calculate the z-score. So z is 58 minus 54 divided by 2, which is unknown, but I gave it to you. So 4 divided by 2 is 2. So now we have a z-score of 2. Now what do we do with that 2? Is it extreme enough? I still don't know if it's extreme enough. That's right. We don't know, but we got a z-score. We can do something with that. We know that this is the sampling distribution of the differences between means. What we can do is break this up by what we know. We know that the null is represented by a mean difference of 0, right? Null at the center. We know that H1 can exist at both ends of the distribution, right? Extreme scores, alternative hypothesis at the tail. We want to get closer and closer to those tails, right? The closer we are to the center, to the null hypothesis, that's more and more evidence for the null hypothesis. We want to get extreme evidence against. So we want to be really close to that green bar. Right now, we found that our z-score was 2. So now we have to figure out, is that extreme enough? But quickly, what if we switch groups? Let's say conservatives aren't group 1 anymore. Let's say liberals are group 1. Conservatives are group 2. So now liberal mean is 54. Conservative mean is 58, still the same, but now one's group 1 and group 2. So now the difference between these two means is -4 if we just simply switch the groups. Theoretically, we should be able to switch these groups and it should still work. So what it implies to us is that there's both a positive and negative z-score value, that the placement of the group should not matter. We're looking for different scores. So we have both a positive and a negative z-score. Essentially, we have 2 z-scores, one positive, one negative. This means that the z-scores are tested on both tails of the distribution, right? When we're talking about extreme scores, we're not just saying it's extreme high or it's extreme low, it's extreme on either tail. So we represent this by saying z is plus or minus 2.0. What's an extreme score? We have to see if our 2.0 is extreme enough to be extreme evidence against the null, extreme enough to reject the null hypothesis. So we need a cutoff score to tell us once you pass that cutoff score, you are now able to say it's extreme enough as evidence against the null hypothesis. You can think of that cutoff score as a finish line. And it's like you're running away from the null, right? You're piling on evidence against the null and you're running, you're running, you're running. You get to the finish line. As soon as you cross the finish line, you're far enough away to say, this is enough evidence against the null hypothesis. We can reject that null. We can say that null and say, we don't need it anymore. we can focus on the alternative hypothesis being more true than the null, or actually the null being more false. But we need a cutoff score, and we compare our calculated z-score of 2.0 to that cutoff score. We can refer to these as z-calculated and z-critical. Z-calculated is the one we calculated. So right now we have a mean difference of 2.0. We also have a z-critical, which is our cutoff score. It's the thing we're comparing with our calculated. Our z-critical stays the same for all of our analyses. It's selected before our analysis starts. We say this is our z-critical value, that's going to be the cutoff. We can change our z-critical and make it more or less stringent, but oftentimes there's an accepted z-critical value, and usually what we do is try to make it more stringent, not less. Again, think about that distribution. You want to get to the finish line, you want to cross it. Once you cross that finish line, we're in extreme territory, it's enough evidence against the null. If you made it less extreme, that's an easier race to run, right? What this z-critical does is it cuts off an area of that standard normal distribution that represents a % likelihood that the null hypothesis is true. So everything beyond that point, that z-critical point on both tails, that finish line on both tails, we can add up the area in those tails to tell us what % likelihood the null is true. Remember, we had cutoffs when we said, 68, 95, 99. That implies cases in the center of the distribution. But if we have 95% of the cases in the center of the distribution, how much % is on the tails? 5, right? If we have 99 on the center of the distribution, we have 1 in the tails, right? That area beyond the tails tells us what % likelihood the null is true, right? So if we have 95, that means 5% in the tails, 5% likelihood that the null is true. We have 1% in the tails, 1% likelihood that the null is true. We can use that thinking of the normal distribution, right? I say here, the area beyond that z-critical on both sides represents the likelihood that the null is true. You want a low % chance that the null is true. Extreme mean differences are demonstrated when our z-calculated is greater than or equal to our z-critical. Again, you have a critical value and you want a larger score than that. So let's say our critical value is 1. Let's say we calculated a z-score of 3. So critical is 1, calculated is 3. 3 is greater than 1. That means we've passed that 1 finish line. We are in this outside region. It's extreme enough for us to say the null is probably not true. We can reject the null hypothesis. Critical z-scores. So how is this selected? How is this critical z-score selected, right? We want to compare our z-calculated to our z-critical. And we want to say, here's our critical. We want to cross that finish line. Same on the other end of the tail, right? We want to, on each side, we're going to have our calculated z-score, but we also have a critical z-score, right? We want our calculated z-score to cross the finish line on either side, be on the outside of them. But how is that critical selected? It's based on what we call alpha. Alpha is selected by statisticians as the maximum allowed probability for the null to be true. We are willing to accept a certain % chance that the null can be true. Alpha represents a cutoff for our rejection region. So alpha is going to be % likelihood that the null is true, or in a proportion, the proportion likelihood that the null is true. Right? And we want a low proportion, right? We want the null to be unlikely. So what we're doing is creating a z-score associated with an alpha level, associated with a low likelihood that the null is true. We said 95 in the center, that means in the tails we have 5%. So let's say that we use that number as our cutoff. That would mean that 95% that the null is not true, everything in the tails, 5% that the null is true. Right? So if I scored beyond that z-score, it would indicate to me that there's a low likelihood that the null is true. You'll see, oftentimes we pre-select an alpha level of 0.05, indicating a 5% chance that the null is true. Applied to our mean difference, 5% of all mean differences will be considered extreme. Some cases are not going to be as extreme, those in the middle of the distribution. Those beyond this score are going to be considered extreme. Alpha also represents 5% of the cases left in the tails. Again, 0.05 maximum likelihood that the null is true. I keep using this example, and that's because it's important. If we recall, we had 68, 95, 99. And we said that's 1 standard deviation, 2 standard deviation, 3 standard deviation. Converted to standard deviation units or standardized units, it's 1 z-score, 2 z-scores, or 3 z-scores. However, we said that's not really 68, 95, 99. It's 68.26, 95.44, 99.74. If we wanted exactly 95, it's not 2 standard deviation units, it's 1.96 standard deviation units. If we wanted 99 exactly, it's not 3 standard deviation units, it's 2.58 standard deviation units. The z-score would be 2.58. So that's important for us because we're thinking about 95% confidence interval, 95% confidence level. That z-score also indicates 5% in the tails. So if we're selecting an alpha of 0.05, that means 5% in the tails, that means 95% in the center, which reminds us that our z-score associated with that is plus or minus 1.96, right? I said that this is already an established alpha level, right? 0.05. We want to find the z-score associated with an alpha level of 0.05, and that z-score is 1.96. So everything we're going to be calculating is going to be compared to a z-score critical of 1.96. So if we get something greater than an absolute value of 1.96, then we've passed that finish line. We're in that region. So alpha is 0.05, 5% of cases extreme. I already mentioned this, but that z-score also represents the rejection region. So another way of thinking about it is we can create this cutoff z-score, this z-critical value. And what it's going to represent for us is once we cross that, we're now in the rejection region, or the region in which it's okay to reject the null hypothesis. Right? We call that the rejection region. The z-score represents not only 5% of cases in the extremes, but it represents the rejection region. It also represents the 5% chance that the null is true. If we have a z calculated that is greater than our z critical, then our calculated mean difference is more extreme than our cutoff for extremeness. Calculated mean difference is extremely different from what is expected by the null, and we can say that this is a statistically significant mean difference from what is expected by the null. And we can talk about statistical significance in these next couple of slides. But first, let me plug in what we've had. We have an alpha of 0.05. That means our critical z value is going to be plus or minus 1.96. So now we compare our calculated to our critical. This z critical of 1.96 spans 95% of cases of the mean, but 5% in the tails. We know that already. This means that 2.5% of cases are at the top end, 2.5% of the cases are at the bottom end, right? 95 in the middle, that means 5 in the tails. If you divide that equally, why? Right? Because it's a normal distribution, equal sides on the mean. 2.5 in the top, 2.5 in the bottom end of the distribution. If we cross this finish line, if we cross 1.96 with an alpha of 0.05, that means that there's only a 5% chance that we would find a mean difference that is ours or greater, right? If we have a score that is already greater than the z critical value, that means that our mean difference is rare, but also that any mean difference, any z calculated score bigger than ours is going to be even more rare. It's going to be more extreme. We have the z critical, we crossed that finish line, we're in the rejection region now. Therefore, once we cross this finish line, we're in the rejection region, we can say we've met the criterion of being extreme enough. We can blame it not on sampling error, but as a true difference that we would find in the population. Therefore, because we crossed the finish line, because we're in the rejection region, we can reject the null hypothesis that there's no mean difference. We're trying to cross that finish line. Once we cross it, we're more extreme than what is our cutoff for the extremeness. We're now in the rejection region. We can now reject the null hypothesis of no mean difference. If our alpha is very small, that means a lower and lower likelihood that the null is true. It's also harder and harder to reject the null. You can think of that finish line analogy. We had the finish line at 1.96, meaning 5% in the tails, and that represents alpha of 0.05. Let's say we changed it to an alpha of 0.01. That means 1% in the tails. That means now we shrink the size of the tails a little bit. So now it's harder, right? It gets harder and harder to get to that finish line, to get to the rejection region. So if you set alpha to something smaller, it's going to be harder to reach, harder to reject the null. There's been a big debate about whether or not 0.05 as an alpha level is important, but why not 0.01? Why not 0.1, something less stringent, right? 10% chance. There's no real answer on that debate. What we've decided on is you don't want to find a z calculated value that is right at the z critical value. So our z critical is 1.96. Let's say we calculated a z and it was actually exactly 1.96. And we said our value needs to be greater than or equal to. So in this case, we've met that criterion, right? We're actually equal to, but we're actually just right at that line. So we've met the bare minimum for extremeness. You don't want to just meet the bare minimum. Now, that doesn't mean go cherry picking and trying to finagle your data to make it seem like it's more extreme. What that means is what you found is probably not extreme enough. It counts, but we want to find things that are greater than that. And I say that because people do what's called p hacking, and we'll talk about p in a few slides, but they'll run multivariate models in certain ways to where it's like, I'm not yet at the 0.05 level, I'm not yet at the rejection region, but I know that this variable is also associated with this. So if I throw this other variable in there, it'll push it to significance. It'll push it into the rejection region. And you're like, look, I made it to the rejection region. So generally what we want to see is the critical value, and you're like way beyond the critical value that there's no question that it's a true population difference. So instead of changing alpha, just try to find differences that are more extreme than that. This is just a table to demonstrate breakdown in the Z associated Z critical values, right? 1.96, 2.58, and 3.29. These are all important because once you start calculating your Z's and you're like, oh, I have to compare it to the critical. If you've already memorized 1.96, 2.58, then you know, okay, if I calculated a Z of 3.3, you already know I beat 1.96 already. I'm in the rejection region. 0.01, we compare our calculated 2.58. 0.001, 3.29. So I said there's alpha. I've also referred to p or p hacking, or you might have heard p values before. And p is different from alpha, but they are sort of related. Alpha, again, is the maximum probability allowed for the null to be true, right? So we set a cutoff and we say, this is the maximum we're going to allow. And oftentimes it's only 5% maximum for the null to be true. We're trying to limit the amount that the null can be true in these cases. P is different. P is a probability representing the actual probability of finding this extreme of a difference given a true null hypothesis. The probability that the null is true in this extreme of a difference, right? So we have a cutoff of alpha of 0.05, but we can calculate a p-value for a specific score. And that's just figure out what that z-score is and everything beyond that score. We said at a z critical value of 1.96 and negative 1.96, we know that 5% are in the tails. Let's say we calculated a z of 2.58. So our critical is 1.96. We've crossed over, we're in the rejection region, so we can reject the null because we calculated 2.58 z. The p-value would represent all of the area beyond that new calculated z of 2.58. We know the area beyond 2.58 already, right? What percent of cases is beyond 2.58? 1%, right? Converted to a probability, that would be 0.01. So while we have an alpha level of 0.05, our exact probability, p, in this case, with a z-score of 2.58, is going to be 0.01. P will be equal to 0.01. What we learned from this is if our z-score calculated is larger than our z-score critical, right? We've crossed over into the finish line. That means our p-value is going to be less than our alpha, right? Alpha is the maximum allowed in tails for the null to be true. Our p-value is going to represent everything left over in the tails. So it represents the area from that z-score to the closest tail, summed up. Okay, so what I'm going to do now is draw out what I mean. Let's say we have this normal distribution. We're going to have so that's going to be our z-crit. It's going to be 1.96 equals negative 1.96. alpha is going to represent everything in the tails of this distribution. Okay, so we can say alpha equals 0.05 equals 5% equals now. What we want to do is compare this critical, or Z value, or Z calculated to the Z critical. And what's going to happen is we want to see, do we get into these black areas? And these black areas are called what? Rejection region. Let's say for us, we got a calculated value of, for example, remember we got a difference of 4 and -4, which translated to a Z-score of 2 and -2, correct? So what we'll do is we'll say Z count equals 2.0. Okay. Then what I can do is take this and draw all the area from my Z calculated value to the end of that nearest tail. And we can say P is going to be equal to the actual probability of finding that extreme of a case or more extreme. So that is the area beyond that point where our Z is calculated. So it's going to be equal to now just from this image, which area is more? The black area or the red area? The black area, right? We see there's a little thin strip on the left-hand side, there's a thin strip on the right-hand side, indicating that the black area is a little bit larger. So what we can figure out here is that if Z count is greater than Z crit, then P is going to be less than alpha. We can add equal to. So if Z-calc is greater than, meaning it crossed over into that finish line, the finish line is Z-crit, the black area. If Z-calc is greater than Z-crit, that means the red area, P, is going to be less than the black area, alpha. So here we can say P is less than alpha. Because alpha is 0.05, we know that P is going to be less than 0.05 because that area, that red area, is going to be smaller than the black area of 0.05. What happens if so I say here, Z-calc is now plus or minus 1.0. Have we crossed the finish line? No, right? We're outside the rejection region now. We're right before. The rejection region is this. Let's go back, change this to black. Rejection region is here. And the black the red line hasn't reached the black line. So because of that, if we add up the black region, it's still going to be, no matter what, it's still going to be 0.05. It's still going to be 5%. But the red region is now what? Is it greater than 5% or less than 5%? Greater than. So now you can say P is greater than 0.05. So what we're learning from this is what we need is a z-score that's going to cross that finish line. Once you cross that finish line, your z-score is greater than your critical value. Your calculated z is greater than your critical z. You're now in the rejection region. Therefore, you can reject the null hypothesis, meaning you have extreme enough of a score, which indicates that you have a statistically significant difference between these two groups. I'll say that again. You cross the finish line, your z-score calculated is greater than your z-score critical. That means you're in the rejection region, which means you can reject the null hypothesis of no mean difference, which indicates a statistically significant mean difference between these two groups. So again, alpha selected beforehand has an associated critical z. P is based on the data's probability of finding this difference or greater if the null is true. We need z-calc to be greater than or equal to z. If z-calc is greater than or equal to z, then the area of extremes, P, is going to be less than the area of z critical. If this happens, then the difference between mean of group 1 and the mean of group 2 is so extreme that we can't blame it on sampling error or chance. Therefore, H naught, or the null, is probably not true, so the z calculated will be in our rejection region, therefore we reject the null hypothesis, therefore P is going to be less than or equal to alpha. And if our alpha is 0.05, we just plug in 0.05 for alpha. So z calculated is greater than or equal to 1.96, then we reject the null, it's in the rejection region, P is less than 0.05. If we had to change this to an alpha level of 0.01, we change out this value for z critical, and it's just 2.58. We change it to P is less than 0.01. And so in our example, we had a calculated value of plus or minus 2.0, right? The severity score between liberals and conservatives. We said, what is alpha? Alpha, no matter what, unless I say otherwise, will always be 0.05. What is P? Well, we can calculate that. If we have a calculated value, our z-calc 2.0, what is our p-value? Recall that the p-value indicates the area at that point and beyond. Should be smaller, right? We know that between -2 and +2, there's 95.44% of cases, right? If we wanted to find the p-value would just be the area beyond that, right? Which would be 4.56. Converted to a probability would be 0.0456. So our p-value as a probability would be 0.0456. And we could say, because we have our z calculated of 2.0, it's greater than 1.96. That means it's crossed the finish line, it's in the rejection region, therefore we reject the null hypothesis. P-value is going to be less than 0.05, which is our alpha. P is going to be less than alpha, which means that P is less than 0.05. And actually we did find that P is less than 0.05. P is 0.0456. When we had this z-score formula of the mean difference, and I said, we never know that denominator, right? Sigma sub x bar 1 minus x bar 2. And I just gave it to you that I just took it for granted it was 2.
Well, what that is the standard deviation of the sampling distribution of the difference between group means, right? So what that means is we're taking two groups, we're taking a sample of two groups, liberals and conservatives, we'll pull them out, we'll take their means, we'll subtract their means, and then we'll throw that into a distribution. Then we'll do that again and again and again, infinity times. And what would happen is we should expect to find, if we did that infinity times, we would find a normal distribution where most differences tend to cluster around 0, but then there's going to be a lot of difference, within that. How do we know the standard deviation of that? We don't, right? We don't know the standard deviation of that distribution because it is a theoretical distribution. Oftentimes we're not going out and taking infinity samples. Wait, how does one take infinity samples? You can't, right? So it's a theoretical distribution. You can get a lot of samples. It's going to take you the rest of your life, but you can't get infinity samples. So this is a theoretical number, right? But we can estimate that. We can estimate that number based on what we know from our sample, right? If we assume that our samples are coming from that population, then we can use the statistics within our sample as estimates of those population parameters, of estimates of those sampling distributions of differences between means, right? So this is just a standard deviation. So we can use our sample standard deviation with some tricks as that number, right? So we have to estimate it. So we never truly know that number. So we estimate the standard deviation of the sampling distribution of the difference between means from our one paired sample. And when we estimate, it's called the standard error of the difference between means. So we estimate that sigma as a standard deviation of the sampling distribution of the difference between means, and this is how we do it. So instead of sigma sub x bar 1 minus x bar 2, it's going to be SD sub x bar 1 minus x bar 2. So what we're really doing here is taking the variability within group 1 and adjusting for the sample size of group 1. Same for the variability or variance within group 1, but we're taking variance, right? So, and if we sum, we square and then put it back in the original units, just like we did with standard deviation calculation. So this is just an adjustment. It's just saying we're taking standard deviation from our group, but our group is smaller than what we would expect from the population. So we're attenuating that standard deviation, right? That's all we're doing is attenuating. We plug this number back into our z-score formula and it becomes all of that. So basically what this is doing, this number itself is trying to identify how much variability is going on between group 1 and between group 2, adjusting for variability going on within each group, right? So between over within. What we've been looking for this whole time is to make sure that group 1 and group 2 are different, truly different. So what we really want to find is a huge difference between groups and less difference within groups. Think back to our earlier example, where we're looking at the example of a gerontologist studying memory recall between two sets of groups, right? One group had recall games that they played on an electronic device, the other one just journaled, right? And we found that recall was better in group A, the first group that had the memory recall games, right? Keeping their memory sharp. Also recall that the numbers were critical for our understanding. So group 1 with the iPad and the recall games had scores that were consistently in the low 80s, right? They never crossed below 82. It was like 82 to 86 or something like that. Group B had scores that were in the high 70s, right? But they never crossed into the 80s. So we saw homogeneity in scores, but there was no overlap, right? Take that to the extreme. We could see scores for the recall group in the hundreds, like 99, 98, 100. And then for the non-recall group, for the journaling group, we could see zeros and ones and twos. So we'd see homogeneity, not a lot of variance within, but then they'd be so distinct from one another that we'd say this has to be a true difference. There is no overlap whatsoever. So that's exactly what we're applying here with this formula, is we're saying, are they distinct enough to be separate from one another and they're not overlapped? But when we adjust, when we use this standard deviation formula, the standard error of the difference between group means, as an estimate for a population parameter, we change the curve. We've been operating under this assumption of a normal distribution this whole time. When we start estimating parameters, instead of actually using those parameters, we alter the curve. It now becomes, instead of a probability distribution, it becomes a t distribution, hence t-test.